So I want to tell you it's a great pleasure for me to be here. Good crowd, that's nice to see. And that's because there's this extraordinary density of folks that do AMO physics, that do, now I'll call it quantum information and so on. And as I said, it's really an honor to be able to spend some time with you. Now, I prefer if you feel comfortable about asking questions during my lecture or talk. And if there are none, there'll be a quiz afterwards. And also, to tell you a little tiny bit about myself, I'm an applied physicist. So I like to do things that I eventually see have a use in principle, even if that use is very far away. Although I will say it was totally accidental that it took 30 years for LIGO to do anything. Until then, nobody knew what it was. So I never told anybody what I did for my postdoc, because, you know, LIGO, what's that? So it's, Atomtronics is among my favorite topics, and it is one of those things that is, I think will eventually be useful, but the question is whether, I hope it's not going to be 30 years, because I won't be here, probably. All right, so the work I'm telling you about is a follow-on from actually a series of works. And though I have just my name here, there's a key figure in the experimental aspects, and that's Brad DiNardo, who's got his PhD last year and was really instrumental in these experiments. And the theory is still underway working with my colleague at JILA, Murray Holland. So Atomtronics is truly a faithful analog of electronics, hence the name. And it's the analog is atom flux substitutes for electric current. And very simply, and almost in a boring fashion, you can think of having a source of atoms and a sink of atoms, and there's an atom flux. It is very much equivalent, or the dual, to electric current. And then chemical potential substitutes for electric potential. So whereas you have a battery you think is the canonical thing that provides electric potential, and you have something that you hook up to this battery called the load, and the function of the battery is to drive an electric current through the load. And the battery's other role, which is far more important than it seems, is to maintain a voltage across its terminals, V terminal. And therefore, we can conceive of an atomtronic circuit that's just like the electronic circuit, and replacing the battery is but I'll still call it a battery, is something that provides chemical potential. And I can imagine something which is a load through which atom flux flows through. And like the battery over here, the job of this battery is to maintain the chemical potential at a nominally fixed value. All right. Well, when I started out, I had a really hard time understanding chemical potential. I mean, you can get electrocuted by electric potential. Who's ever gotten too hurt by chemical potential? Only if you let the hydrogen cylinder tip over under high pressure. You'll recall that the change in internal energy of a thermodynamic system is given by, in general, or for our purposes, three terms: internal energy, a term that has to do with the entropy and temperature, a term that has to do with the pressure and volume, and a term which has to do with the number of particles. And indeed, the chemical potential is the energy required to add a single particle to the system. So I have some system, I want to add a particle to it. How much does it cost me if I keep the entropy and the volume of this system the same? And what's interesting is, for a finite temperature, the chemical potential of finite temperature gas, the chemical potential is less than 0. But for a BEC, a Bose condensate, the chemical potential is positive. And it's not just the sign. There's a lot interesting that's going on with that positive chemical potential. All right, so you saw the title. It's something to do with Atomtronics and something to do with an oscillator. I want to start with some things that you probably know, and then add some things that you may or may not know, but are purely classical. All right, so let's talk about the driven oscillator. So the classic driven oscillator, well, let's start with a an oscillator not driven yet, consisting of a capacitance and inductor. This has a resonant frequency given by 1 over the square root of the capacitance times the inductance. And you know that if I get this thing started, say with a voltage across the capacitor and then let it go, that this thing will oscillate with current flowing back and forth between the two devices with this resonant frequency. But you also know that any physical oscillator, such as an LC circuit, such as a pendulum, etc., has some dissipation. Well, eventually its oscillation will die down, and that's represented by this resistor in the circuit. And so why not, to make this, to get rid of this dissipation, why don't I add something which has just a negative resistance to compensate for the positive resistance? Then the thing ought to go forever. And this concept of negative resistance is very powerful. And if you look up, especially in old texts about oscillators, they think in terms of negative resistance. And in microwave circuitry, one often thinks in terms of a negative resistance. And that's because negative resistance is closely related to gain. And we'll see that in a bit. But by just compensating for this, you can achieve sustained oscillation. Negative resistance. Okay. So some device examples of negative resistors, again, purely classical in a sense. It's a classical device, but in fact, it's a quantum device, which is a tunnel diode, as an example. And I'm going to guess that you can imagine what a tunnel diode does, or something has to do with tunneling. So if I draw, this is current versus voltage, so this is an IV curve. And something like this is a typical tunnel diode IV curve. And this region in which there's a negative slope, well, a resistor, I should have drawn it here, is just a straight line. A normal resistor is just a straight line, but a tunnel diode is nonlinear and has this region in which the slope is negative. And so if I take a system and bias it in this region, then there's a corresponding negative resistance, and sometimes appropriately called differential resistance, because it's just the slope of this curve, where the slope is positive in a lot of places. Right here, it's negative. That's an interesting region. And if you do a search under Google saying tunnel diode oscillator circuit, you'll find a figure that looks like this. And I want you to show how many parts it has, the same ones we already know. There's a inductor and capacitor, so this is called a tank circuit, and it will oscillate at this frequency over here. There's a parallel resistor for a variety of reasons I won't go into, but we can just think of it as the dissipation resistor. There's a battery, which provides a bias voltage. Strictly speaking, these two aren't quite the same because there's a voltage divider right here, but enough of that. And then there's a tunnel diode. Very simple circuit. And the great things about this is it oscillates at very high frequency. In fact, another example, oh, by the way, so if this negative resistor is larger in magnitude than the dissipation resistor, that's gain. The system will break into oscillation, and that's what's called the driven oscillator. When the off state is unstable and it wants to oscillate, that's specifically a driven oscillator. When you push your kid on a swing, that's called the forced oscillator, because you're doing it in time with that. So that's the driven oscillator. Another example is a gun diode. Rather similar characteristics, but is used to generate up to terahertz frequencies, for example. Very simple circuits with these. And these are very quantum mechanical, by the way, but certainly classical circuitry. And then there's transistors. And I'm going to be very interested in transistors. And let's talk about the canonical transistor. Here's the first one. I should say it's a model of the first one. The transistor was invented at Bell Labs, for which 3 guys won a Nobel Prize. Hopefully you've heard of them. But it's a 3-terminal device in which a small voltage or weak current controls the large current. And on average, there are 2 major flavors, the bipolar and the FET transistor. The bipolar, a current controls a current, and in the FET transistor, a voltage controls a current. These are only DC pictures, by the way. At high frequencies, microwaves, for example, there's no point in saying whether it's voltage or current controlling the current. It's typically a wave, and it's has a complex impedance, and so it's a combination of IV, if you like, that controls the current. Well, given that there are over 500 billion transistors that have been manufactured since 1946, surely they're good for something. And your smartphone has 2 billion transistors in it. So a transistor is evidently a really important device. And in particular, a transistor provides gain and thus enables amplifiers, oscillators, switches, memory, logic, radio, Wi-Fi, and smartphones, et cetera, et cetera, et cetera. So this is one of the reasons I'm so interested in transistors for Atomtronics, because they're ubiquitous functions in electronics. So do I think they'll eventually be, possibly, in Atomtronics. Now, if oscillators were a little bit familiar, and maybe a little bit boring, batteries are really boring, all right? But I'm going to tell you something interesting about batteries. That's that 1.5 volt battery, you know, you're sticking, does anything actually have a battery you replace anymore? I think so. But most of it's rechargeable. It doesn't matter. They do all the work. Because any non-trivial circuit is a non-thermal equilibrium system. And the battery is what works against the circuit staying in thermal equilibrium. And when the circuit comes to thermal equilibrium, you throw out the battery and put in a new one. All right? So, so the energy used to do work or information processing is provided by a battery or what have you. You can plug a circuit into the wall, I know. But I'm just going to talk about a battery. And there's an internal resistance that is fundamentally associated with the battery. It's not a matter of technology. It's not a matter of, you know, just improving things. If you have something that supplies energy as a battery and tries in particular to keep its potential constant across its terminals, it has dissipation, information dissipation or energy dissipation, what have you, but there's an internal resistance. That's going to be very important to us. So battery always has an internal resistance regardless, and that's why the terminal voltage in general is different from the battery voltage. Because when there's current flowing, there's a drop across this internal resistor. And if you know the internal resistance, it dictates key properties of the circuit as a whole. For example, the maximum power supplied or work that can be provided to a load is given by the battery voltage squared over twice the internal resistance. In other words, you can deliver maximum power from a battery when the load resistor equals the internal resistance. It also has to do with how much information processing you can do in that same sense. Well, there's going to be power dissipated in the internal resistor, and a flashlight, nowadays you can get LED flashlights and you feel them heat up, and that's because there's an internal resistance because the LEDs don't get that hot, but the batteries get hot these days, and that's given by the current flowing to the load squared times the internal resistance. And this is really important. If we're going to have a supply of atoms and they're ultracold, and there's heating, even though I didn't do anything, so to speak, there's heating, then maybe the atoms don't stay ultracold. And there's generated noise. This is Johnson noise due to this internal resistance, and that's also fundamental when you have a finite temperature. There's also going to be quantum noise, but this is all classical stuff. All right? So batteries are a bit more important to understand when you're working in the ultra-cold regime because things are going to heat up because you're doing some work or you're doing some information processing, and your atom supply is actually going to get hot. So, and in fact, any battery, therefore, supplying cold atoms at a fixed chemical potential also has corresponding internal resistance, just like the electric one. But the interesting thing about in our case is that the internal resistance is negative when supplying hot, that is, say, non-condensed atoms, and you get cooling, and that's known, that's what happens in forced evaporation. The hot atoms leave, the remaining atoms get colder, and you represent that by a resistor, which is negative. But it's positive when you supply ultra-cold, in particular condensed atoms, then you get heating. in your supply of atoms that heats up. All right? All right. And so the next thing is we usually think of most classical circuits that we build as classical entities. But let's look at the transmitter. A transistor provides gain. As I said, there's lots of things you can do with it, like make an oscillator. And this is a classic transistor oscillator. All oscillators have the same components. Something that defines the resonant frequency. Here is a capacitor, an inductor. All right. In this case, the transistor uses its three-terminal property to take some feedback into the, in this case, bipolar, to the base. There's a bias voltage here defined by these two resistors and this battery. And of course, we need a battery to supply the energy. So this is a classic, it's called the Meissner oscillator. And it's actually, for how many components here, it's an incredibly simple circuit. And now, if I attach an antenna to this thing in the right way, this thing will emit an electromagnetic wave. That's another thing that you know, at least in principle. The thing is, so my PhD advisor had his 80th birthday the other day and had a chance to give a talk at one of the events. So I had a couple of things at that event to remind him of how much he taught me, or how much he didn't taught me, but I learned later. If you look in the book Quantum Optics, there's this chapter 2 section, Radiation from a Classical Current. The point is that this thing is surely classical in here, but this electromagnetic field is as quantum mechanical, in my view, as anything, including entanglement, but we can talk about that later. It emits a coherent state of the radiation field.
Okay, now, usually, I mean, you've said something rather provocative here, because usually when we talk about emitting a coherent state, we say this is the paradigm of a classical field.
Yep.
And you're saying that it's quantum.
Absolutely. The whole field, as you know, used to be called what? Quantum electronics. Why did they call it that? Because so I would say, and the tunnel of diodes and all of that. And that's right. And therefore, this current that's actually here is actually entangled, but only very briefly, right? As long as the carrier lifetime, which unfortunately is very short, so you never notice it. But later, we're going to see, if we decide to have a discussion, how the atom equivalent is much more, the relationship between what's going on here and here is a little more intimate. And you can see how there's, or at least you can acknowledge how there might be entanglement. All right? So I know that this language, but I would say this is as quantum as the world gets, as long as I call it photons, right?
Okay, but you are saying something that is not in the canon of...
Absolutely. Of quantum 2.0. You are right. But if I'm going to be consistent when I move over to Atomtronics, you'll see a much closer relationship. All right? But I would say that, for example, a coherent state of atoms is a pure state. And I don't know anything more quantum mechanical in some sense than a pure state. But maybe you'd argue with that too.
Well, of course, part of the problem, I mean, we probably don't want to get into
Yeah.
this, but part of the problem is that in a certain sense, some of us do want to.
Yeah.
Well, I mean, you did invite questions.
No, I love it. Okay.
And the snickering that happened from the back of the audience was because they knew that I would rise to the bait.
Yeah.
So part of the problem with coherent states is that in a certain sense, they're right on the edge. You only have to do a little bit to a coherent state to make it quantum in the usual sense. I mean, the usual, well, look, there's a lot of usual ways in which people define what's quantum and classical about an electromagnetic field. But one of them is, can you make it with a classical distribution of charges and currents? And if the current there that's going through that
It's purely classical.
is classical, then this field must be classical according to that
Absolutely.
On the other hand, you only have to do a little bit to that coherent field to turn it into a non-classical one. Whereas a thermal field is classical, you got to do a lot before that may be, or at least that's typical.
So I agree. It's on the edge in the following sense. With a coherent state, particularly of atoms, with a coherent state is an entropy and a temperature. And it's very hard to assign entropy and temperatures in general, well, entropy to the side, to temperatures to many quantum states, you'd like to say.
So
yeah.
You're confusing me even more, because if I actually had a coherent state, which you just said is a pure state, if it's a pure state, I would say its entropy is 0 and its temperature is 0.
Yeah, that's not right. But,
Okay,
but okay.
Great, so you'll tell us why.
Yeah, well, I don't have to go off on that, but over lunch, I'll show you why. Okay, yes. Has to feel it, absolutely. It's just that it forgets, yes, except forgets very, very quickly. All the quantum action in these circuits, tunnel diodes, everything, are absolutely quantum mechanical, but the circuit forgets about it very quickly because the electron hits the lattice and so on, scatters, and that's it, right? All right, so now I'm going to talk about the transistor. And all of my interest in Atomtronics started years ago, thanks to especially the Air Force who put up with it. We wrote this paper 2007, but we've been thinking about it since 2004, ultracold analogs of electronic devices. Except in this paper, we thought of literal analogs of semiconductors, and then we realized later that we didn't have to get so fancy as to have crystals and so on. Instead, we have something that's relatively simple. It's a triple well structure. So here's a well, and here's a well. And we copy the FET nomenclature of having a source, gate, and a drain. And barriers and biasing is defined by magnetic and optical fields. So this longitudinal parabolic structure is determined by magnetic fields. So this is potential here. This is longitudinal position here. And then we form the barriers optically. And furthermore, we put on what's called the terminator. You've used a 50 ohm terminator. This is also terminates so that this potential which rose up is flattened effectively. In other words, atoms that find themselves here are essentially, from our purposes, coupled to the vacuum rather than coming back into the system. So we have this terminator beam, so it's resonantly tuned to the atoms. And it's very useful to remember, you tend to think in terms of these pictures of atoms sort of flying over the barriers. And maybe atoms will be here and they're sitting down low. It's very useful to have a different picture. This is a contour of a fixed potential. And so in some sense, looking down on this potential, you have the source, gate, and drain regions. And it's a cigar sliced by laser beams. And effectively what they do is they squeeze the potential by the source gate and the gate drain to form these two barriers. But atoms flowing from the source to the drain have to go through the gate. And we'll see later that there are gate atoms sitting here. And so source atoms which flow here collide with atoms that are sitting in the gate. Not surprising in the end, but it's just useful to keep this picture in mind, as this one is in some ways misleading if you think of it as a spatial picture. So just to tell you how we do this experimentally, we use an atom chip. So this is glass and silicon substrate. And you can define where it's transparent, so it has a window right there, and where it's silicon, where it's all black and it's silicon. And it has 60 UHV-compatible electrical feed-throughs. That turns out to be incredibly handy. On the other side, the vacuum side of the chip, because it's going to separate ambient from vacuum, it's also metallized, and the window provides very high numerical optical access to the atoms. And zooming in on this structure right here with a little bit of poetic license, there are atoms that are caught and formed a BEC right between these two wires. And on the edge view, we take a microscope objective. We can shine a laser beam to focus laser beams onto the atoms. And so, for example, here's a single barrier represented by a single optical beam focused onto this cigar-shaped magnetic potential. And by the way, we can also image this lens, so we got great resolution. So here's a density plot of the potential. This is atoms when they're a single barrier above the critical threshold, just so you can visualize what the thing actually looked like. So this is an in situ picture. These atoms are about 750 nanokelvin, just above critical temperature for this trap. In the case of the transistor, we use a pair of barriers generated by an acoustoptic deflector driven by an arbitrary waveform generator. And these are old experiments, by the way. When we talk a little later, it's going to be a little bit different shape, but this just to, again, establish the baseline. So now we have two barriers. Here's a density plot of the potential, and here are atoms above the critical temperature, just to show you what the system looks like, illustrated by being filled with atoms. All right? Now, we're going to do some experiments, and first I'm going to show you some old experiments. So with the terminator on, the drain is flat. And then we put atoms in the source at a given temperature and chemical potential. In these first experiments, we start with the gate totally empty, no atoms there. So as I said, the terminator effectively couples atoms that might get into the drain to the vacuum, so they won't reflect. And the gate well is empty. And then we start with these barriers very high. And then when we lower them, we call that T equals 0. Then we let the system evolve for some time. So atoms can go from the source to the drain, source to the gate. In principle, if they get into the drain, they go away. They can bounce off the barriers. The barriers are different heights in our experiments. And after they flow for a different time, we do some absorption imaging, which we do either in trap or in time of flight to measure their temperature, to get time of flight data, to get the number in the condensate, the number in the thermal cloud, the chemical potential and temperature of the cloud. And let me tell you about in-trap absorption imaging, because this is a little bit subtle. So the system is allowed to evolve for some amount of time, milliseconds. And then before snapping a picture, in what I'm about to show you, we turn off this terminator beam. All right, so there it goes away. And then we wait about 5 milliseconds in these first examples. That gives the atoms exactly the right amount of time to go from about here to the classical turnaround point where they'd be reflected. So in this picture that we have, you'll see the atoms clunked at the turnaround here, but actually there are atoms this whole way, and that needs to be very clear. You won't see too many because they're moving very fast. Let's say they're rising up the hill, so they're moving very quickly. Slow down, slow down, slow down. They reach the top, and they would normally come back. But in this first set, we take a snapshot right here. But there are still atoms always coming out, so we really get the whole thing. You'll just see them clumped here. But first, a word about our energies. All energies here are given in frequency units, kilohertz. So you know how to convert kilohertz to energy. And you know how to convert energy into temperature. So there's a thermal frequency. And to give you characteristics, the barrier heights are about 30 kilohertz. That's going to be a big number here. And temperatures corresponding to 1 kilohertz would be at 50 nanokelvin. Actually, in these first experiments, we're as low as 250 nanokelvin. So it's about 5 kilohertz or so.
What's the trap frequency? Just the large number.
67 hertz.
67.
Right, or 70. Later, it's higher, about 100 and something.
So the temperature is roughly equivalent to the excitation frequency.
So the barrier heights are much higher than the barrier energies are much higher than the thermal energy, first of all, and chemical potential. Well, here's all the energies of this experiment we're about to see. So the barrier heights are here, and the kilohertz. Temperatures are typically 5 kilohertz. This is the gate frequency. It's around a kilohertz. The transverse frequency is a little more than a kilohertz. So here's a typical picture of in-trap imaging in this experiment. So you see the drain atoms at the classical turning point. And again, that's because this is where they're going slow and turn around. But actually, you can see a wisp of atoms the whole way. So I said it's low density over here because they're moving quickly. The remarkable thing is that the gate is initially empty, but it develops a condensate at the bottom. And I'm not going to go into that much. I'm going to take that as a given by now because this is true with a semi-classical treatment that treats the atoms as particles. Semi means though we allow BEC. And this is rather remarkable, but it's ultimately due to the fact that there's very strong population inversion as atoms go from the source into the gate, and then collisions cause them to fall down and form a condensate. And that was a surprise when we first saw that. In fact, the theory says that the atoms in the gate are at a lower temperature but higher chemical potential than they are in the source.
How substantial is the condensate fraction?
In the fraction in the gate,
Like how much of them
actually, we don't know. It's extremely difficult to actually make quantitative measurements on the gate atoms. However, the source, that's just given by their temperature and chemical potential, so it varies through these experiments. But it's something like initially 50% of the atoms will be in the condensate, that only the non-condensate get over, right? So now let's talk about the transistor oscillator. But here's a couple of questions. What is the Atomtronic analog to the electronic oscillator? And in electronics, we know that voltage and current vary sinusoidally in time in an oscillator. So evidently, the chemical potential and atom current, maybe they should vary sinusoidally as well. What is the Atomtronic analog to the coherent electromagnetic wave, if there is an analog? We know the electric and magnetic field now vary sinusoidally in time as the wave propagates. What is it that happens in the Atomtronic analog? What is the analog to electric field and likewise vary sinusoidally in time if there is an analog? All right, we often think of the Matterwave as the wave function. But here I'm interested in something that's a little more closely analogous to the electromagnetic wave. So how are they different?
Now, one of the things that's different that you sort of glossed over here is that the whole story you told about transistors at the beginning was classical. And now we learned that in the gate there's a condensate. Well, that's not much analogous to what happens in a transistor. We don't have condensates in transistors. We don't have superconductors.
Well, there certainly is.
Naturally, I mean, you have a whole superconducting thing, but that's not what you've been telling us.
Yes, none of this, there's no, so we're not doing a superconducting analog, we're doing a classical analog, absolutely. And your next point was?
Well, you're telling us that the things condense, so it sounds like if we wanted a faithful analog, that we should be talking about superconductors on the electrical side, but you have.
So good point. Associated with a condensate is an energy. You agree? Yes?
Well, there's chemical potential, if that's what you mean.
In fact, if a condensate spontaneously forms in a gate, just as we would say for a laser, though I don't want to confuse those two, already I've got an oscillator because they're started out empty, and now I have the ground state of the oscillator evidently excited when there's a condensate. All right, and so let me think of the gate as my LC circuit. All right, and that gets excited. Likewise, the gate acts like an oscillator. That gets excited, excited in a sense, gets populated. We think of the ground state. Okay. All right, so in these, now I'm going to switch the potential a little bit. Here's my source, gate, and drain. But I still have two barrier heights, and they do have to be different, but I'm not going to go into that today. But now I put on a large potential bias onto the source. And I do the same thing. I fill it with fixed temperature and chemical potential. But now I can, whereas before, I was sitting down here and had the atoms hot enough so a few would go over. If I make these very cold and there was no bias, I wouldn't get any atoms to go over the barriers. But now I can have very, very cold atoms, and some of them can make it over the barrier. More importantly, I'm going to say that these are very cold, and what do I mean by very cold? So I mean two things. Thing one, let's talk about the barriers. They're Gaussian in shape. And if I ask about atoms being transmitted or reflected by this barrier, of course, if the atoms come in at very low energy, so here is the potential in kilohertz versus position. Here is the transmission versus energy of the atoms. At very low energy, of course, they'll be reflected from the barrier. At very high energy, of course, they'll get over the barrier. And the lovely thing about Gaussians is it's a very simple function where the width in going from 0 to 100% is inversely proportional to the width of the Gaussian over here. Narrow Gaussian, the slower this step is. Broad Gaussian, the broader this is. And most interestingly, you get exactly 50% transmission and reflection when the incoming particle has energy equal to the barrier height. And if you learn one thing from this, it's the properties of a Gaussian barrier. Very simple. All right? So we call this the tunneling region when the atom's energy is below the height of the barrier. But actually, this whole region is non-classical in this whole region because even above the barrier, some are reflected. So now let's suppose that I have on the left side of the barrier atoms at a fixed chemical potential and temperature. And I can ask, what gets through to the other side of the barrier? Well, for our experiments in the Gaussian widths, here is the energy of a barrier, 30 kilohertz. And if the atoms are at a temperature of 2 kilohertz, most of the atom flux on the other side is classical. Most of the atoms are getting high over the barrier. But if I cool them down more, then I have most of the atoms get through the barrier by tunneling. And at very cold, 38 kilohertz, or 0.38 kilohertz, 380 kilohertz, hertz rather, then essentially all of the atoms getting through are via tunneling. There's a small tail that are thermal. All right, so by very cold, I mean the temperature is characteristic, a temperature below which is this characteristic tunneling width of the barrier. So the other thing that I mean by cold is, of course, the gate is actually quantized. In our case, there are about 25 levels which are trapped between these two barriers, effectively no tunneling. But at the very top of the barriers, atoms can tunnel out of them. And if I look at this, actually, so this is energy versus level, it's actually fairly harmonic. And so when a BEC is there, for example, I can think of it staying in a harmonic oscillator. It's not strictly harmonic. Actually, here's the difference in energy. It starts at about 1 kilohertz. It has tighter and tighter spacing, but gets looser and looser again because these are at first concave and then convex in shape. And in fact, we tune the barrier separation so that the first and last trapped energies are degenerate. And so a typical temperature at which atoms are below, the temperature is below this barrier, this gate level separation, and are within the transmission tunneling region of the barriers, that's what we mean by very low, those two things. All right, so we do this again with an acoustoptic deflector. And truth be told, we can only do this to some limit. So we bias the source by using a blue detuned laser beam, which is scanned over the source region. And here are the barriers. So this is the optical intensity that goes on top of the magnetic intensity. And ideally, we could go off to the left infinitely, but we can't. And so the actual shape of the well has a little dip in it. I'm not going to talk much about it, but it just explains why you'll see atoms out here. Those technical limitations. So experimental, these are just numbers. Again, we have typical same barrier heights, 30 and 31 kilohertz, about the same order anyway. The source bias is 25 kilohertz, so we've really broadened this well. And then we bring down atom temperatures to less than a kilohertz now. And the sequence in the experiment is a little different than earlier. At earlier times, we leave the terminator off the whole time for short time of flight times. And then after 8 milliseconds, we turn on the terminator for 8 milliseconds and allow the system to evolve for different sets of wait times for the current to flow before taking a picture. So in each case, after 10 milliseconds, the terminator is on for 8, and then we watch the flow after that. All right. And with the way we treat this theoretically is we treat the gate as a harmonic potential and only consider the upper 2 levels. The upper 2 levels are coupled to the source, and only the last level is coupled to the gate. And that's what our theory is based on. And the ansatz is that what happens is when the BEC forms here, it doesn't really stay in the ground state. It wants to oscillate, back, physically, mechanically oscillate back and forth as a dipole mode. And so the ansatz in the theory is that the atoms are in a coherent state, alpha, with a fixed number of atoms. And so the whole thing bounces back and forth. It doesn't really want to sit in the ground state. It wants to be in a coherent state. So again, this is like your LC circuit that's oscillating, not yet in what's happening with the transmission. And then we have various annihilation and creation operators. I'll get back to that later. Let me show you the experiment. So this is a bunch of in-trap absorption images at various times, from 0 to 20 milliseconds in 2 millisecond steps. Even at 0 milliseconds, because the time t equals 0 is not that well defined, you see some atoms beginning to flow out into the drain. And then at 2 milliseconds and 4 milliseconds, now the time that it takes in this experiment for the atoms to reach the turnaround point is just about 4 milliseconds. So then at 6 milliseconds, you see them starting to pile up. At 8 milliseconds, piling up even more. You don't see many atoms here because they're moving very quickly. So, but that's to keep in mind. It's not as though they're gone. They're just much dimmer. Then remember, after 8 milliseconds, I start turning on the terminator for 8 milliseconds. So we're taking snapshots with the terminator on in each case for only 8 milliseconds. And so in this picture, atoms have had time to go out and come back and go out again. So taking one full round trip and almost 1.5 round trips. And then here's 12 up to 20 milliseconds, always seeing them about here. And then here's the gate. You see atoms filling the gate. And then here are the atoms in the source, of which there's always a condensate in the source. To compare, let's get rid of the first source gate barrier. So we only have a gate-drain barrier. And this is the same set of circumstances for taking snapshots. But you'll see a characteristic difference both in the output in the drain, which tends to be more intense but also more smeared, and a different shape, a different character to the source. So is there coherence? Well, the first one, and I'm going to be fairly brief about that. So this is 14 milliseconds oscillator versus the single barrier system. that there's quantum coherence, and we've got three nice pieces of evidence, in the drain output is evidenced by the diminished thermal speckle in the drain. So if you have atoms randomly coming out with no coherence, you'll get something we call thermal speckle. It's a little bit analogous to the speckle you see from this laser beam if it was blown up. Random places where the output interferes to give you something that you can see, and here not much at all. But there's more. And how about coherent state? So let's talk about what happens with a coherent wave, for example, when it's reflected. And remember that this matter wave is coming out with particles that are about the barrier height, or slightly under, about 30 kilohertz or 31 kilohertz, right? So that's a carrier. But this coherent oscillation of the BEC is about 1 kilohertz. And we'll talk more about that, but let me just point out one thing. If you have a wave incident on a mirror, and this is later going to be the classical turning around point, something that reflects, we know that what comes out the other side is first inverted and then returned. And there's no intensity, if you like, at the reflection surface. And that's because of the interference between the forward and reverse propagating wave. They cancel there. You can say, well, what is the separation between this node and the antinode? It's given by the wavelength over 4, or the distance between nodes is the antinodes, rather, is the wavelength over 2. And it's also a little bit useful when you get down to the details to remember matter wave in free space, the phase and group velocities differ by a factor of 2. That's a reminder, and that's, in fact, the phase velocity is half of the group velocity. So we have a matter wave that has a carrier of 30 kilohertz, and a periodic modulation we'll establish later is at the BEC frequency. And interference according to the carrier, interference occurs according to the carrier frequency, but also the fact that it's modulated. And therefore, the period of the modulation is what tells you where the interference is going to be. If an electromagnetic wave travels really fast, the atoms go nice and slowly. So if you're asking, what is the intensity I see of atoms at the mirror, so to speak, what I'd see is, I'd first see the intensity rise up, but as interference occurred, I'd see it go to 0 at the mirror. On the other hand, if I looked at an antinode somewhat behind the mirror, at first I'd see the incoming wave and its intensity rise up. And as the reflection came back, I'd see constructive interference, and I'd see the intensity increase, really by a factor of 2 instead of whatever factor I've shown here. Okay, good. So if I look at what happens here in time, early times to late times, notice that you see atoms, here's the classical turning point marked on the graph here. And notice that the atoms that first reach, and some of them surpass the classical turning point. That's because initially they're thermal. But as the system reaches a quasi-steady state, you don't see atoms at the turning point. You see them here to the left. And that's actually the position where you'd predict the first antinode to be. And that can only occur if these things have coherence at the millisecond, that is, as the oscillation frequency of the condensate that's in the gate. So the initial atom flux includes a thermal component, but as the wave makes its way to the turning point, which arrives at about 3.2 milliseconds, after 6 milliseconds, they've had enough time to get back, and after 8, even a third time to give a stronger interference pattern. And so this is an indication that it's a coherent wave. And the other thing to notice is the structure in the source, which maintains a condensate and this narrow behavior, which I might have a hard time explaining in a short time. But let me give you first, qualitatively, an equivalent circuit for the system. So the drain current, the current that goes into the drain, let me get back here, thank you, is derived from source atoms whose wave function is almost purely longitudinal. So there's a big source well, and only those that are going very much longitudinally manage to get into the drain. Atoms with a large transverse wave function act as a battery. In other words, collisions allow the transverse modes to be converted into longitudinal ones. But the transverse modes, hence, act as a battery. So we can have a circuit which takes into account the source bias, and then a battery which corresponds to atoms that have a strong transverse component in the source, but then there's, of course, an internal resistance. And then the gate then provides what looks like a negative resistance to the system because there's a resonant frequency, supports dipole motion of the BEC, which couples atoms that are going straight through from the source of the drain. And that we'll see gives a negative trans resistance. So if that's true, let's take a look at the source well temperature dynamics. So these are at two different starting temperatures. In this case, this is about 38 nanokelvin here. And here's time t equals 0. This is the temperature of source atoms as a function of time, transverse temperature, and longitudinal temperature. The longitudinal temperature of the atoms in the source goes down in time, reflecting a negative resistance. The transverse temperature goes up in time, suggesting dissipation. And hence the circuit model that has the internal resistance positive, but a resistor which connects, a differential resistance which connects the source and the gate and then to the drain is negative. All right? So during oscillation, the source well temperature evolves so that the transverse temperature goes up, the longitudinal temperature goes down, and that's exactly what one would take from this model. And then there's theory, and I'm not a theorist, so maybe you're going to be grateful for this. But it starts with a many-body description of the gate well, and then we can't do a many-body model of the whole thing. We treat the rest in terms of a circuit model. As I said, the key is the ansatz is that at very low temperatures, a BEC forms at the gate. That we know even from semi-classical theory and experiment, but not in its ground state, but an oscillating coherent state. And what happens is, so that's the ansatz, when you work out that theory, is that atoms which traverse into the drain interact with this oscillating condensate with an interaction energy. And I will skip ahead. I'm glad to talk about this over lunch. But if this seems strange about this interaction energy, actually the physics is almost identical to the work that was characterized by Marlon Scully and his colleagues of having a microwave cavity and an incident atom in the excited state, as an example, will either be transmitted into the cavity or reflect just because of the interaction between this atom and the vacuum state. And the physics is identical because this atom here interacts even with the vacuum state, but it's a little easier to see if this is an excited state. And it has, in this case, if I'm in a pure excited state initially, it has a 50% chance of being reflected or transmitted. So only one of two, or every other atom, if you like, makes it into the gate, and it only makes it into the gate if you consider this upper state as a linear combination of symmetric and antisymmetric modes of the superposition of these two states, symmetric and antisymmetric depending on the phase relative to the electromagnetic field in the cavity. One phase transmits and the other phase reflects. And the same thing happens to us. So first you can have an atom reflect if it doesn't have a right interaction energy. And if a condensate is oscillating in the gate, the atoms coming in can interact and leave and partially reflect. Or likewise, you can transfer, you can transfer energy into or out of this dipole. But in either case, the ability of an atom to get through and interact depends on a relative phase of this, if you like, of what comes in versus the oscillating dipole in the same way as it does for a microwave cavity. And so there's a coherent gain that is a result of phase-sensitive interaction energy. Again, sorry to be brief in that. And it's this interaction energy which, first of all, allows a lot larger flux of atoms through these two barriers. So if I only look at these last two levels and there's no interaction energy, the only thing that would get through the gate are those atoms that have an energy that is resonant with either of these two levels. And since these are fairly high Q, you get very little flux. On the other hand, when there's an oscillating condensate in interaction energy, it turns out you can get a much broader range of energies to be transmitted through the drain, but in a way that's phase-locked to the way that the condensate moves. Don't know why that happened. Magic. Okay? So it's this interaction energy that, first of all, gives rise to gain, and then also gives rise to a coherent output of the atoms in the drain. Coherent because their interaction with the condensate is also coherent. So I think I'll just move on here to say Atomtronics is a faithful analog of electronics where atom flux substitutes for electric current and chemical potential substitutes for voltage. A driven oscillator utilizes gain/negative resistance to maintain a steady-state circuit oscillation. An Atomtronic transistor consists of a triple potential well having a narrow gate coupled to much broader source and drain wells. By the way, the difference in barrier height plays a key role in dynamics. That's a good lunch topic as well. And the circuit behavior is established through coupling between an oscillating BEC and the gate and atoms lying in the source well that then, due to their interaction with the gate, get coupled over into the drain. And that actually is very similar to the way a p-n junction works. And the source gate presents a negative resistance, and internal resistance associated with transverse source well atoms limits the current flow. And this is actually what establishes a steady state in the same way that there's a resistor typically in series with the battery to limit current flow in an oscillating electronic circuit. And I'll just stop there, and sorry I pulled it short on the theory. We can talk about it more at lunch. Thank you.
Thank you very much.